In mathematical analysis, we often confront smooth, continuous curves that are notoriously difficult to evaluate directly. By breaking these curves down, we can translate them into infinite, distinct, and discrete polynomials. These infinite polynomials are power series. They serve as the critical bridge connecting discrete algebraic sums with continuous mathematical analysis. By reducing complex functions into sums of simpler terms, power series provide the foundation for solving differential equations, formalizing Taylor analysis, and building complex analysis. Understanding power series is essential. It gives mathematicians the machinery needed to take abstract continuous phenomena and convert them into calculable discrete mathematics. These equations on page 172 formally define a power series. Equation 2 generalizes this, showing a series centered at a specific point, A. Within the structure, the Cn term dictates the coefficients. These are the fixed constants defining the exact shape of the series. This theorem from Chapter 3 establishes the radius of convergence, denoted as r. Using the limit supremum of the coefficients, we calculate the exact boundary determining where this infinite sum is mathematically valid. If we map this onto a one-dimensional number line centered at A, the radius r gives us an interval of convergence, stretching outward to a minus r and a plus r. Inside this interior interval, the series converges absolutely. Outside, in these exterior regions, the series diverges, meaning the sum fails to converge to a finite value. The exact boundary points, where the distance from the center equals r, are unstable zones. Convergence here is not guaranteed and requires specific analysis for each case. A power series is a strictly bounded topological space. Within this precise radius, infinite sums safely behave like finite polynomials. This raises a question for calculus. Can we legally treat an infinite sum exactly like a standard finite polynomial when calculating derivatives? Theorem 8.1 in the text provides the clear answer. These equations show the original series, equation 4, and its term-by-term derivative, equation 5. While the series converges everywhere inside R, it only converges uniformly on a compact subinterval located strictly inside the main radius, shrunken by epsilon. Applying the root test proves the derived series maintains the same convergence boundaries, from negative to positive R. Because the convergence is uniform on this compact subset, the rules established in Chapter 7 apply. This uniformity is what permits us to interchange the derivative operation and the infinite sum. Consequently, the formal power series coefficients are directly connected to the function's derivatives at the center, matching the Taylor series coefficients. Uniform convergence is the specific mechanism that maintains the validity of calculus operations as the number of terms approaches infinity. Inside the interval, the operations are entirely predictable. However, we must also carefully examine what happens at the boundary points. Theorem 8.2, Abel's limit theorem, defines this behavior. This equation evaluates the limit as the variable x approaches a specific boundary point, such as x equals 1. If a point approaches the absolute boundary from the inside, and the series manages to converge at that specific edge point, the values align exactly. The function does not break at the limit. Its continuity extends seamlessly right to the edge. The proof for this theorem actually relies on the partial summation formula, or a summation by parts, established earlier in Chapter 3. Power series are resilient. If they converge at a boundary point, their analytical structure remains intact right up to that edge. If we need to evaluate our series near the edge of its original domain, we face a mechanical problem. We have to recenter the expansion. Theorem 8.4 addresses this problem directly. Equation 17 shows the expansion of a power series about a completely new point, A. Geometrically, if we start with a circle of radius r centered at 0, we can select a new point A inside it. A new circle centered at A expands outward until it touches the original boundary line. The proof involves rewriting the initial term algebraically and expanding it using the binomial theorem. This creates a double summation. Swapping the order of this double sum is justified by the absolute convergence proven in Theorem 8.3. A power series contains the mathematical information of the function throughout its domain. It can be transplanted to any point within its radius of convergence. This brings us to the rigid nature of power series compared to standard smooth functions. Theorem 8.5 is the identity theorem. This equation proves that if two power series agree on a specific set of points, their coefficients must be identical. A standard smooth function can fluctuate and return to zero. A power series curve locks into a specific trajectory. If two series share a set of agreement points containing a limit point inside the interval, they align identically. By defining a difference function and utilizing the recentering technique, we prove that all coefficient differences between the two series must be zero. The behavior at a single microscopic limit point dictates the structure of the entire series. Power series are inherently mathematically deterministic. Knowing a fraction of their behavior reveals their infinite form across the entire domain. We can now apply this machinery to one of the most important functions in analysis. This equation defines the exponential function, e of z, purely as a power series. Applying the ratio test to its coefficients proves that its radius of convergence is infinite. By utilizing the Cauchy product of absolutely convergent series, we arrive at the fundamental addition formula. E of z times E of w equals E of z plus w. The familiar properties of exponential growth are derived directly from the topological rules of infinite series. By establishing these rules, we lay the groundwork for complex analytic functions and Fourier series. This chapter builds the bridge uniting discrete algebraic series with continuous calculus operations. Uniform convergence on compact sets establishes the mathematical conditions required for term-by-term calculus. The identity theorem proves the rigidity and determinism of analytic functions. Power series transform complicated functions into simple infinite polynomials, providing one of the most elegant and powerful techniques in mathematical analysis. If you enjoyed this detailed explanation of Rudin's principles of mathematical analysis, please like this video, subscribe to the channel, and turn on notifications for more chapter-by-chapter explanations of classic mathematics books. Share this video with your friends and continue your journey into higher mathematics with us.